Our alumni from National Taiwan University, Department of Atmospheric Science. So the first one, Po-Lun, my good friend, who is a research scientist in PNNL. And he is also the Chem 5 Aerosol liaison. Today he will talk about this, the title as you can see here. So let's welcome him.
Thanks, Minhui. I want to take a minute to thank the organizing committee for having me here. It's really nice to be home. And today I'm going to talk to you about actually the resolution sensitivity of aerosol-clouds and aerosol-cloud interactions in global climate modeling. And I want to first acknowledge my co-authors. And the first one is Phil and Mingwai Wang, who is going to be a professor in Nanjing University next year. Hailong Wang in PNNL, Steve Gan, PNNL, Xiaohong Liu in University of Wyoming, and Richard Dick Easter, Bill Gustafson, and Simona Tilmas in NCAR, and Xiyan Ma, who is where? Oh, there, okay. In Livermore, who helped me with the year of tropical convection analysis. Yun Zhang, Steve Klein, and Robert Pincus helped me on the cloud simulator. Phil gave the introduction, so I can go through these first few slides pretty quickly. That currently in the global climate model, we have several known biases in terms of aerosol and aerosol forcing and aerosol distribution. The first one is the fact that you can take a look at this plot. The gray area and the black line is the medium and the range of all the aerosol models simulated black carbon concentration. And the purple line is the aircraft measurements. And you can see that the model underestimates the black carbon concentration near the surface by at least 1 order of magnitude and overestimate the concentration at altitude by 1 order of magnitude. And the other thing is that the near surface concentration in the Arctic, this is a barrel in Alaska, and the black line represents the long-term average black carbon concentration. This is a seasonal cycle, and the yellow line is the standard model. And the model is at least 2 orders of magnitude too low in the winter time, and it's 1 order of magnitude too low in the summertime, and it has the wrong seasonal cycle. And the same signature is in another Arctic measurements. And we try to understand what's the problem, and our group has done a lot of different, tackle this problem from a variety of different aspects. And I have been working on to see if the increasing the horizontal resolution can make a difference. And we, in an earlier paper that we did, we found that the aerosol transport is actually very sensitive to resolution. And this is the eddy kinetic energy, 1 degree normalized by the 2 degree results. And you can see the eddy kinetic energy in the 1 degree is about 15% higher than the 2 degree model, and that results in a lot higher black carbon transport by the eddies in 1 degree compared to the 2 degree model. And another very known problem is that the models tend to have high estimate of aerosol indirect forcing. This is a figure taken from the Roman et al. 2010, and this is the estimate of aerosol indirect forcing, and as a function of papers being published, the result being published, and you can see there are really a very large range of this quantity, and Chem 5 is around here, which is at the high end of the compared to all the other models. So if we want to know if aerosols, these problems can be improved, the biases can be reduced with increasing resolution, but running high resolution global model is very, very expensive. So at first we want to do a test bed. So we developed this tool that provides the consistent physics and forcings for dynamical downscaling. So we first port all the physics from CAN 5, including deep and shallow convection, turbulent boundary layer, microphysics, cloud macrophysics, and aerosols. And we use the same emission inventory to drive both CAN 5 and WRF. We port all this package from CAN 5 to original model WRF. And the boundary forcing of WRF came from the global model simulation that includes meteorology, aerosols, and chemistry. And so this way we introduce a dynamical downscaling framework, and we can increase the resolution in WRF and run in a relatively short period of time, but with a more frequent instantaneous data output. So, and directly compare with field campaigns measurements and so forth. And the only thing different will then be the resolution between the two models. Of course, there are other differences like the die cores and other numerics, but at least this way we eliminate the factor that the two models have different physics. So that's good. And we compare the model simulated AO. What's this? This is surface black carbon concentration with the observations, and these are all the model simulations. And you can see that the model underestimates the black carbon concentration by 2 or 3 order of magnitudes originally, but then in this period of time, there's an aerosol plume coming from Asia and like this, going to Alaska, and barrel is roughly around here. And you can see that in CAN 5 doesn't have this plume, but in high resolution WRF starts to successfully simulate this plume, and that caused a very big jump and actually reduced the bias compared with observations. So we think that although all simulations greatly underestimate the background surface BC, but episodic transport events are better resolved in high-resolution model. And so why are the models not able to simulate the background aerosol concentrations? And one possibility is that there have been papers that says there are basic problems with the emission inventory that we use. There are local emissions in the Arctic that's being ignored in the IPCC-R5 aerosol emission inventory, and that's a possibility. And we can also compare the model with the aircraft measurements, and it gives us basically the same picture that all the simulations underestimate aerosol concentrations at altitude. Here, I want you to focus on these. Well, this is very hard to see because it's so colorful. But this is CAN 5, result 2-degree CAN 5, and this is 160 kilometer, 80, 40, 20, and 10 kilometer resolution. Domain average cloud fraction is all about 20%, but with increasing resolution, you can see that this filament of aerosol plume starts to form, and it actually is able to deliver the aerosols into the Arctic. And at this snapshot, the black carbon concentration at barrel increases from 0.3 nanogram per kilogram to 96 nanogram per kilogram. So it's a very big difference. The other thing is that although the cloud fraction, domain average cloud fraction is about the same, but you can see that this aerosol plume actually is going through between the two cloud systems. There's a cloudless transport pathway in the high resolution, which is not observed in the coarse resolution model. So So two things are happening. One thing is that in the high resolution, the aerosols becomes more concentrated and much higher concentration. And the other thing is that the aerosol plumes and the clouds becomes less collocated. Therefore, aerosols are less subject to cloud processing and vice versa. And after this, we calculate this so-called cloud susceptibility, which is the fractional change of cloud liquid path to the fractional change of aerosol optical thickness. And we found that with increasing resolution, this susceptibility of clouds decreases by about 40% from 160 kilometer grid spacing to 10 kilometer grid spacing. And after this work, we found that it's time to evaluate these things in the global model. So we do this CAN5 simulation running at 2 degree, 1 degree, half degree, and quarter degree with specified dynamics that we use the year of tropical convection, high resolution analysis to constrain the model meteorology with some model calibration. So we can talk about that offline. And we use MEM3 as our aerosol model that includes 6 different species: black carbon, primary organic matter, sulfate, sea salt, dust, and secondary organic aerosols. And here I want to point out that first you can see that the aerosol concentration in the Arctic between the 2 degree and the quarter degree model is a lot different, maybe about an order of magnitude different. And the second thing is that Phil also mentioned earlier, we can see much more filaments in the high resolution model. And these filaments are associated with the better resolved synoptic scale eddies. And we see similar features in cloud and precipitation fields as well. And we write down instantaneous model state variables and process rates along a trans-satellite track instead of writing it everywhere in the globe, and I will say that a little bit in detail later. And 2 weeks ago, we had a visitor to PNNL, it's Kerry Emanuel, and he made a comment I thought is really good, so I wrote it down here. He said from 2 degree, actually he said from 5 degree to quarter degree resolution. What's really happening is that we are going from poorly resolved to well resolved eddy, and we are going from parameterized to poorly resolved clouds and convections. And the last one is that we know that aerosol cloud interactions remain parameterized and in subgrid scale. And lastly, I also use the cloud simulator along the satellite track, and I'll show that in a minute. And to evaluate the global climate model, people have conventionally used long-term averages or instantaneous values over the globe. But there's a possibility that it's comparing apple to oranges. So this is the H-trans satellite constellation, and you can see they have their daily pass around 1:30 p.m. every day. And so I was wondering, so if we write out 6 hourly data and then compare them to satellites, there might be a sampling bias. And how important is that? We really don't know. So instead of doing that, maybe we should use a satellite simulator to take measurements of the model atmosphere like this. So how important is the sampling bias? This is the 4 different resolutions actually give you very similar results. So let's just pick one and focus on it. The black line, this is the PDF of the aerosol optical depth measured. The black line is the observation, which comes from Calypso. And the other 3 lines are from the 6 hourly output, or if we do the orbital sampling. And the red line is the orbital sampling plus we discard samples from the model where at the time and the location where satellite doesn't have a successful retrieval due to clouds or a bright surface and so forth. And you can see that 6 hourly and orbital sampling give you basically very, very similar PDF, but if you take into account of they call this satellite algorithm failure in our model sampling as well, it reduces the bias and agrees with the observation better. So this is important. But we actually didn't, there's something missing here. That is, we didn't use the same algorithm that Calypso used to retrieve the aerosol optical depth. So we are currently developing an aerosol LiDAR simulator, and this simulator package will be used in Aerocom and CMIP communities, so to provide a better and more consistent comparison with satellite observations. And what about clouds? So I was actually pretty surprised that if we this cloud sampling, I think this is the PDF of cloud optical depth, and the sampling strategy of 6 hourly samples, orbital sampling and orbital plus sampling basically give you very, very similar PDFs. Those are the lines you cannot distinguish them actually. But you can see that they all overestimate the cloud optical depth. This is the mean value in the parentheses, and they all at least 50% larger than the observations. So if we take into account the fact that the algorithms are different, so I enable this COSP simulator. So it uses the same algorithm to derive the cloud optical depth from the set of cloud state variables that's in the model. And we can found that this pink line here, and it reduces the bias in the lowest cloud optical depth regime, and here it still overestimate the frequency of occurrence, but you can see the bias, the mean bias is reduced dramatically. And so at this point you can see that it really matters a lot in how you evaluate your model, and sampling and algorithm strategies matter. And so I was not able to finish the last aerosol indirect forcing estimate due to different ways of doing this. But we can see that it will have an impact. Okay, let's come back to increasing resolution. And we found that these are the words are really small. This is the black carbon, zonal mean black carbon burden, color integrated burden, deposition, and northward transport, and the transport efficiency. And here you can see that with increasing resolution, we start to have higher aerosol concentration in the mid-latitudes, and also a lot higher, maybe more than 50% more northward transport of aerosols. And we further did a decomposition of this transport term and into the mean stationary AD transport, transient AD transport, and we found that it's the it's the transient AD that's making the biggest difference. Is actually this term, and when you have higher resolutions, the ADs are resolved better, and the AD transport of aerosols are also much better. And remember the previous plot, we showed that the model underestimate the black carbon concentration near the surface, and with increasing resolution we have at least a factor of 2 improvement, but it doesn't entirely change the picture. So that echoes what Phil said earlier. Increasing resolution can help, but it's not the only solution. There are more things we need to do. And these analyses are included as part of the aerosol diagnostics package. And this plot is that I compare the PDF of LD from model simulations and against Calypso's observations. These are all along the satellite track. And globally, you can see that all models agree with the observation pretty well, and this means that we tuned the model pretty good. And there are some areas that we know that huge biases, like these 4 green boxes: Arctic, North America, East and Central Asia, and North Pacific. You can see that we overestimate the low ALDs and underestimate the high ALDs. And we think that it might be related to the underestimation of emissions in East Asia, and that affects all these other regions as well. And these three blue boxes are basically the marine aerosols, tropical Pacific, South Pacific, Southern Ocean, and you can see that model actually overestimated high ALDs, and we think it might be related to the fact that the current model only treated sea salt aerosols for marine aerosols instead of considering both the sea salt and organic aerosols. So some people in our group is also working on that to address this problem. And this is an interesting behavior I want to share with you. And because aerosol optical depth is a radiative property, so it actually, you can have the value for daytime and nighttime, and Calypso does report both daytime and nighttime. Of course, the algorithms are different, and in the nighttime you are not, it's not being hugely affected by clouds as much. But let's ignore that for a minute, and let's assume this is a true diurnal cycle, that we have a higher daytime ALD and lower nighttime ALD. You can see that the 2 degree and 1 degree model, we actually have the wrong diurnal cycle, and half degree and quarter degree model starts to show the correct diurnal cycle. So this is intriguing, and we want to understand what drives the diurnal cycle. Of course, this analysis is not done yet, so this is just hand-waving right now. We came up with, actually, I came up with the first 3, and Phil came up with the last one, and I did a quick and dirty analysis, and I think the first 3 are not relevant, so I was wrong for all 3 of them, and he was right for the last one. And it's not a very happy thing for me. Anyway, so we know that there's a diurnal cycle of surface wind, which contribute to the mobilization of sea salt and dust aerosols, so that can contribute to the diurnal cycle. And with the diurnal cycle of clouds and precipitation, that's the removal mechanism for aerosols. And the relative humidity that affects the water uptake, and lastly, the diurnal cycle of how aerosol transport out of the boundary layer, because when they are out of the boundary layer, they are no longer subject to cloud processing or segmentation and these things. Anyway, I just thought this is interesting. And I'm going to quickly go through this. This is surface PM 2.5, and with higher resolution, you can see consistently we have lower estimates of low PM 2.5 and high estimates of high PM 2.5. Okay, so let's now take a look at this big problem here, the resolution sensitivity of aerosol indirect forcing. And we use the methodology, the decomposition methodology that Steve Gann proposed and published in 2013 to calculate the aerosol direct, indirect forcing, total aerosol forcing, and this is the zonal mean. And although you can see the global mean value, but for the 2 degree model is 1.74 watts per square meter, and the difference between the 2 degree and quarter degree is only 0.3. It's really small, but the signal actually all comes from this mean latitude area, and if you pay attention to this, this is actually scary. This is almost 3 watts per square meter difference in this area. So this is a big forcing term. And so we want to understand what drives the resolution sensitivity of the aerosol indirect forcing. So we did some detailed analysis, and this is the aerosol indirect forcing. The four lines are the 4 resolutions, and these are well, let's ignore this, but you can just consider this as the dynamical regime, whether it's convective or non-convective. And you can see the first term is the aerosol indirect forcing, the second plot shows the difference of droplet number concentration between PD and PI, and this plot is the difference of droplet nucleation process rates between PD and PI, and the last one is the cloud lifetime difference between PD and PI conditions. And so you can see that there are we have consistent resolution sensitivity in all four of them, and the largest resolution sensitivity comes from this panel, actually the cloud lifetime. That means with more aerosols, with aerosol forcing, in the coarse resolution model, the cloud lifetime actually is increased much above a factor of 2, I'll say, more than the quarter degree model. So we then used the meanwhile Wang's methodology in 2012 to calculate cloud susceptibility, which can be used to probe the first and second indirect effect. And we calculate this term, the relative, this is the effective radius versus aerosol optical depth, and this is the fractional change of cloud optical depth to the fractional change of aerosol optical depth. And this is the so-called SPOP, or probability, precipitation probability susceptibility to aerosols. And with this direction, direction going up means when you have the aerosols, it induces less precipitation. This means the cloud becomes more opaque. This means cloud becomes smaller. And the data that you use for this observation, AODs from CCliCS, effective radius, cloud optical depth, and liquid path is from MODIS. Cloud fraction comes from CCliCS plus cloud set. Precipitation flag comes from cloud set. And I use cloud simulator for all these cloud quantities and aerosol optical depth and precipitation from CAM5. And you can see that the observation shows that the real world, let's say, has a much weaker or smaller cloud susceptibility to aerosol forcing as compared to this to the models. And this term, the precipitation probability susceptibility, has an order of magnitude larger susceptibility compared to these two terms. So you can see that actually the second indirect effect is dominating, is overwhelming the first indirect effect. And so the last point I want to make here is that we found that increasing resolution actually enlarges the first indirect effect estimates, but reduce the second indirect effect bias. And the reason why it makes this larger is that we also found that in the quarter degree resolution, we have, well, first you have higher concentration for aerosols, so one possibility is that it becomes saturated. And the second thing is that we found the subgrid vertical velocity becomes larger, so that it produces more droplet more easily. And how reliable are these satellite retrieved quantities is a big question. And many people will argue that the effective radius retrieved from satellites probably not very reliable, and the precipitation flag probably is much more reliable. But I'm not the expert of this, so I'm just repeating what other people told me. Well, then it's interesting to discuss why the second indirect effect is reduced with increasing resolution. Here is the removal timescale of cloud liquid condensate, you can see that, or you can consider that as a liquid cloud lifetime. In the 2-degree model, it's about 17 minutes, and in the 1/4-degree model, it drops to about 30 minutes. And we then analyzed their two removal mechanism, which is accretion and autoconversion. And you can see that, and this accretion fraction from the 2-degree model to 1/4-degree model, it increases from maybe 0.4 to 0.55. And it's because with increasing resolution, you have an increase in both accretion and autoconversion rate, but accretion rate increases faster. And so with increasing resolution, you can say that there's a shift of regime from autoconversion dominated to accretion dominated regime. And we know that the current model formulation is that the autoconversion is a function of aerosols and accretion is not. And why is this happening? So we want to further understand it. We found that it's actually from the fact that, well, when you go through all these slides, you'll see that all these findings are so obvious. So with the higher resolution, we already know from the beginning that the eddies are being resolved better. And with the better resolved eddies, we have a much more frequency occurrence of strong moisture convergence. So the moisture convergence becomes more stronger and more concentrated. And that causes the higher condensation rates. And that results in a higher frequency of occurrence for stronger accretions than the autoconversion. And then we are going to maybe skip this. And this is the plot that shows that this is the accretion average over 4 resolution simulations, and then take the annual average. This is the autoconversion. So you can see on average, autoconversion is larger than the accretion. That's how the model is doing right now. But this is the standard deviation of the 4 resolution simulations, and then take the annual average. And you can see that and this is for the autoconversion. So you can see accretion has a higher resolution sensitivity than the autoconversion. And the geographical dependence actually is linked to this term. This is the moisture convergence averaged over 4 resolutions, and this is the standard deviation of the moisture convergence. So we then want to see whether the model, the high resolution model that that produces a stronger moisture convergence is realistic, or is just a problem. So this is the frequency of occurrence of precipitation, and this is the mean of the precipitation events, and this is the standard deviation from a high resolution observational data and the 4 resolutions. And you can see that with increasing resolution, the models start to agree with the observations better. So now but although you can, from this PDF, you can see the large bias still exists, although increasing resolution does help. So to summarize, we found increasing resolution partially reduced some known biases, like the low estimate of aerosol concentration in remote regions, high estimate of aerosol indoor forcing, low estimates of high pollution events, etc. And large biases still remain, even in the highest model resolution here. And we think that it's, of course, important to address these model uncertainties associated with model physics, with boundary forcings, and increasing resolution reduces the cloud lifetime effect bias, but increases the cloud albedo effect bias. And this is because increasing resolution leads to the change of balance of physics, shifting the warm cloud precipitate regime from autoconversion dominated to accretion dominated regime. And this regime shift then is further linked to the more condensed, intense moisture convergence at high resolution. And this high-resolution moisture convergence and precipitation agrees with the observations better. And lastly, I want to say that, sampling and algorithm biases should be accounted for while evaluating the model simulations against observations. Thank you.
Please. You mentioned, maybe you said it's a field ID in terms of the higher resolution makes aerosol break out of the boundary layer. Have you looked at the vertical wind speed when you increase resolution? How that changes?
Well, there are, this is suddenly become too loud. There are I know of two mechanisms. One is resolve the vertical transport, and the other is the subgrid convective transport. And I did find that with increasing resolution, the subgrid, the convective mass flux happens less frequently but stronger. So I think, that's why. But I didn't do a full evaluation yet, but just from this, I start to believe that his hypothesis is more likely to be the reason.
Can you say more quantitatively the vertical transport when you increase resolution?
Yeah, I think the frequency of convective transport becomes less frequent. I think it might be 10 or 15% less than the 2-degree model, but the magnitude becomes maybe 30 to 50% stronger.
Oh.
But the resolve scale, vertical velocities get much stronger at high resolution also.
Yeah, that's intuitive.
Yeah, that's intuitive.
Okay, thanks.
I have a question about the autoconversion and accretion. So oftentimes these microphysics parameterization is parameterized, the coefficients are parameterized for to work at a certain resolution, like 1 degree or 2 degrees. So when you run the model at a higher resolution, usually people will retune these coefficients so that they keep the mean state the same. But in your comparison here, you're using the same coefficients. So some of the processes here may not be relevant at the higher resolution. Can you comment on this?
Well, this is, we had a decision, an executive decision to make at the beginning of the experiment design. Well, first of all, one of the reasons for doing this exercise is actually also to understand the behavior of the model physics in high resolution. So if you change the tunable parameters, which in CAN5 there are maybe 80 of them, and then when you see the resolution sensitivity, you really don't know what's causing these things. And so we then decided to keep them all the same and to see how they behave differently in different resolutions. So I think in terms of autoconversion and accretion, there's one tunable parameter there called in the Moyes and Gettleman paper, they call that the enhancement factor, which basically tunes the strength of the autoconversion. And I did try the different several different values, but I cannot. I don't know how to explain the results when they are different. But all I can say is that when I use different coefficients or different values for the parameters, then of course the values will change, but the trend and the general behavior is the same.
Hi, Po-Lun. I'm always puzzled by this increasing spatial resolution. I suppose when you increase the spatial resolution, you also need to shorten the time step, right?
Yes. But
so how do we differentiate between the relative contribution of the two?
So this is also an interesting question then, because another group member actually is exploring the time step sensitivity. And so we acknowledge that. So actually, all the 4 model simulations, or 4 resolution simulations are done at the same time step, which is 15 minutes. But the default 2-degree model time step is 30 minutes, but the 1/4-degree model won't run with 30-minute time step. So we have to reduce it to 15 minutes, but then we keep all 4 resolution simulations the same time step.
Similar question, but also, so the time to reach the equilibrium state will be the same for the 4 different resolutions, or it will be dramatic different? The time to reach the equilibrium state.
Equilibrium in terms of what?
Energy balanced.
Yeah, so do you want to comment? So this set of exercise is done to understand only the physics, and we are not at the point to say how they will do in the climate modeling yet, because that's the limitation of using the Nagin or specified dynamics methodology. So we are only looking at the short timescale physics and fast physics.
I think we can stop here and then let's thank Dr. Ma again.
Thank you.